Hello everyone, welcome to Introduction to the Momentum Conservation and Navier-Stokes Equations. I'm Hugo, and this video is a continuation of the previous video where I talk about the mass conservation or continuity equation. So the continuity and momentum conservation equations are the most used equations in computational fluid dynamics. So that's what I wanted to make two separate videos explaining these two laws, these two equations. So in this particular video, I want to focus on the derivation of the momentum conservation equation. But first, I need to explain some very basic concepts which are important to understand the physical origin of this equation. I will be talking about Newton's second law, and then we will derive very quickly, mathematically speaking, the momentum conservation equation, how these equations are expressed in Cartesian coordinates. And then I will briefly mention some potential applications to these equations. So first, let's start with Newton's second law. So we know from our physics lectures that Newton derived three basic laws of motion. So the first one says that an object at rest will remain at rest, but also an object in motion will remain in motion at constant speed unless external forces act on the body. So when this occurs, the momentum, which is defined as, I define it here as P, capital P in bold letters, is going to be equal to the product of the mass of the body multiplied by the velocity of the body. So according to Newton's second law, the momentum of the body will change according to this equation. So the momentum will vary in time. But remember, momentum can be expressed as the product of mass multiplied by the velocity. And this variation in momentum is going to be caused by forces acting on the body. So we can have multiple forces acting on the body. So that's what I express it on with this symbol, which is the sum of the forces acting on the body. So you can have n forces present. So yeah. So in a few words, this equation tells us that the change of momentum with respect to time is equal to the sum of the external forces acting on the body. So this is actually a vector equation. So in Cartesian coordinates, and let's assume that there is only one force present on the system. So Newton's second law can be reduced to these three equations. So we have the component x, the component y, and the component c. And we have the force, the component of the force in x direction, the component of the force in y direction, and so on. So these equations that I showed you are used to describe solid body motion. But what if we wanted to study fluid, the motion of fluids? So we need to derive equivalent equations for volumes of fluids. So in order to model fluid motion accurately, we need a mathematical operator that can let us describe the acceleration that a fluid will experience when it moves. So this mathematical operator is known as the material derivative, which is represented as follows. So we have this symbol, this derivative, is known as the material derivative, and A can represent physical quantity. It can be, for instance, a scalar, such as the temperature or the concentration of a species in a mixture. Or it can be also a vector quantity, such as momentum. In our case, we are interested in deriving the material derivative for the momentum, which will be P. So this derivative can be expressed as the sum of two derivatives. So we have a temporal derivative of the quantity A, and we add this derivative, which is known as directional derivative. So I will explain this concept to you in a second. But here you can notice that U appears, so the velocity of the fluid will be multiplied by the gradient of the quantity A, which in our case is the momentum. So this material derivative is probably a new concept for you. So this derivative is used in fluid dynamics because of the momentum of a volume of fluid. So the momentum for a fluid, we define it as the product not of the mass but of the density of the fluid multiplied by the velocity. So the momentum in a fluid will not only vary with time, the momentum will also vary as the fluid moves through a space. So this concept is important, this derivative is important because we will consider two derivatives, one with respect to time and a directional derivative, which will take into account the spatial variation of the momentum in the direction of the fluid velocity. So this is why we are multiplying it by the velocity. So this is called directional derivative because the momentum or the the quantity A will vary spatially, and then we take into account the direction as the fluid is moving. So this material derivative is also known as the Lagrangian derivative or as the hydrodynamic derivative. So let me go back and explain a bit more about this equation. So this material derivative actually considers two systems of reference. For instance, this first derivative, which is the temporal derivative, is considers the Euler system of reference. So that means that we take the variation of A in a point. How, let's say, we want to study how the velocity varies in a channel. So we fix a point in the channel, let's say the entry, the inlet of the channel. So we fix a point there. So we study how the quantity A or the momentum, the velocity, will vary in that specific point, how it will vary with respect time. But on the other hand, we have the Lagrange system of reference, which considers variations with respect the movement of the fluid. So it's a mobile system reference. So in Lagrange, instead of fixing a point, we focus on a fluid element. So as I said before, there is a fluid flowing through a channel. So we will take a volume of fluid to study. So we focus on studying that particular volume of fluid. And then we will measure how the velocity varies in the volume fluid, not in the whole channel, but not in a point, but within the volume of fluid. So I will explain also these concepts in a second, but I just want you to take this idea. So the momentum or this material derivative is associated with the convection process. Convection is a mechanism of transfer of a quantity. It's a mechanism of transport of a quantity, which can be momentum, can be temperature, can be concentration. So convection studies the transfer of this quantity from one place to another one due to the movement of the fluid. So we are interested in studying how the quantity will vary, especially in the direction of the flow, as the fluid is moving. So, for instance, an example of convection can be, for instance, the transport of someone or something due to the fluid motion. Let's assume that you are the quantity A, so you take an electric stair. So you are in a supermarket, so you want to go to the floor. You want to go to the second floor, but you are in the first floor. So you take an electric chair. So you go into the electric chair. So the electric chair is going to transport you from the first floor to the second floor. So you are moving as the electric stair is moving you to the top, to the second floor. So we can calculate your material derivative because your position is changing in time, but you are moving also with the velocity of the electric stair. So that's an example of what is the physical meaning of this particular derivative. So let's express this material derivative in Cartesian coordinates. So for the momentum this derivative can be expressed as follows. So remember that volt u means that we have a vector quantity. So this is actually a system of three derivatives. So we have in x direction this term. We have for the y direction, we have this huge term, and for c the same. So you can see that only the symbol, only the index of the velocity is changing. But as you can see, you can notice that these derivatives are very complex because they involve a lot of terms. So we have, for instance, let's analyze the the equation for the material derivative in x direction. So we are studying how the velocity in x direction is going to vary with time, but also we are studying the spatial variation of this velocity field. So the velocity in x direction is vary in x direction in the direction of the velocity in the same direction in x. So the three index are the same, but here you can notice that it's slightly different. So the physical meaning is different. So we are studying how the velocity in x direction is vary in y direction as the fluid moves in y direction. And here we also have something similar, but at the same time it's different. So we are studying how the velocity in x direction changes in c direction as the fluid moves in c direction. So this is just the physical meaning of the derivatives. We need to analyze each velocity, each component of the velocity in each of the directions of your system of coordinates. So yeah, we have here the velocity field in y direction, how they vary, how that velocity component varies in the three directions of the system coordinate, and the same for c. And now I want to move to to give an introduction to some basic concepts. So let's assume we are interested in studying this volume of fluid, which is going to move with velocity u in this direction. So this volume element of fluid also has this element of fluid has a volume which can change with time. Also, that means that we also have a surface. This element of fluid has a surface which can also change with time, and then we have a vector n which points out in this direction n. Yeah. So let's calculate. I want to estimate the total momentum within this fluid element. So remember, if you remember from my previous video, that in order to obtain the total momentum, you have to sum all the quantities, in this case of the momentum, over the whole volume control. So we integrate a volume integral of this quantity, which is the momentum as we defined it before, the product of the density multiplied by the fluid velocity, and then yeah, we sum over all these elements. So once again, so we have this whole volume of fluid, and then we can split this this whole volume in small volumes, and then you will obtain a local momentum. And then if you sum all those momentums from the small volumes, you will get the total momentum in the whole volume. So that's just the physical meaning of this equation. You can do something similar to the force. As I said before, there are forces that are acting on the volume control of the fluid that can cause a change in momentum. So we want to estimate the total force that is being applied in this volume control. So we sum as a volume integral of the product between the density and the force, which is a vector quantity. And if you sum all these contributions from the forces that are acting on the bodies, you will get the total force in B. Now quickly want to explain two more concepts. So the first one is the concept of stress. So stress, in a few words, is defined as force per unit of area. So let's assume we have a volume control of a fluid. So it can be a liquid. So this is a cube. So you will be applying a force over this area. So this area can be computed as the product of this length multiplied by this length. So the stress over this area is just simply the force you are applying over here, and the ratio of the force you are applying over here and the area of this area. So the stresses, this is the total stress. The total stress represents all the forces, all the stresses that are acting on the body, which in this case are 9. So here T, the stress, the total stress, is being represented as a ball quantity, which is not actually a vector quantity, it's a matrix, a tensor. So a tensor is a mathematical representation of all these components, which is just simply a matrix of 3 per 3 components. So the total stresses that are acting on a fluid can be split in two contributions. So the first one is the pressure of a fluid. So when a fluid is contained in a recipient, so let's say you have water in a glass of water, so the liquid will exert a perpendicular force on any surface that is in contact with it. So it can be the walls. So the fluid particles will flow in all directions and provide the same value of pressure in all directions. So that's the basic concept of pressure. But then you also have a second quantity, which is known as the stress tensor of the fluid. So here is sigma. Sigma is also a tensor. It can be a matrix of 3 per 3. So sigma, there is a stress tensor for each fluid in the world. So the stresses that are characteristic of a fluid such as water are going to be different compared to the stresses of another fluid such as chocolate, paint. So the stresses are not always the same for all fluids. So we need a model, an equation that can represent the stresses of each fluid, of each of the fluid that we are studying. So also, yeah, I want to mention why these two contributions are important, is that the stress tensor of the fluid is associated with the dynamic part. So when the fluid is on the flow, when the fluid is moving, this quantity is going to be more relevant. But when the fluid is at rest, we only have the pressure term. So if the fluid is at rest, the stress, the total stress, is going to be the equilibrium pressure. So this I is known as the identity tensor. So stresses are going to only appear in the diagonal elements of the matrix. I will show you some equations in a second where you can see these quantities expressed mathematically speaking as matrices. But I will show it to you in a few slides after this one. But now I want to explain also these concepts quickly. So the first index, you can see that we have the 9 elements representative of the matrix or the tensor, the total stress tensor. So the first index is associated to the normal pointing out over this surface, and the second index or the second indice means the direction of the force. So here we are applying a force in this x direction, so we have x, and we are applying this force over this area where the normal is pointing out in this direction. So we have the stress xx and txy. So doing something and a similar analysis, that we are applying a force over this area, so the normal will point out in x direction, but the force now is being applied in y direction. So that's why we have this element here, and in C we have another contribution in C direction. So the force is being applied in C direction, but the force is being applied also over this surface where the normal is pointing out in x direction. So now let's quickly analyze this area. So now the normal here over this area will be pointed out in y direction. So that's why y appears in the three elements here over here. But now the force here is being applied in y direction. So that's why we have the contribution tyy. Here the force is being applied over this direction. So we have tyx. And similarly, the force is being applied over C direction, but the normal is pointing out in y direction. So we have the stress Tyc. And you can do similar analysis here, and you will notice that, that this figure makes sense. So the pressure and the stress tensor of the fluid are internal or surface forces. That means that the higher the surface, the stronger the force. So the higher or the longer, the higher the value of this area, we will have a higher value of these forces. Also, I want to say that the pressure is always associated to the normal stresses. So that means components of the stress of the total stress tensor with equal indices. So the pressure will always point out here in will contribute to this quantity, but also to this quantity and to this quantity. So that's why the identity tensor appears here. And yeah, so we have here internal or surface forces, but we might also have external forces or volume forces, such as the gravity, which means that the higher or the heavier the fluid is, the higher the contribution of the gravitational forces to the changes in momentum will be. So our momentum balance, how can we obtain a differential equation or an integral equation for a momentum balance? So remember, momentum balance is based on Newton's second law. So if you remember what I said in my previous slides, that we have the total volume, but Newton's second law describes the variation of the total momentum with respect to time. So we include our concept of the material derivative because we are interested in changes in space, but also in spatial changes in the direction of the flow. So that's why we will introduce this derivative here. So we are interested in studying the variation of the total momentum in both temporal and spatial variations. So this can be seen as an acceleration, a global acceleration of the fluid. So this global acceleration is going to be equal to the forces acting on the body, on the fluid element. So we have the contribution from the external forces, which can be volume forces, such as the gravity. But then I skip some steps, and then I represent the internal forces at this, which is the divergence of the total stress tensor, which is this quantity. So I skip this step because it takes some time to express this. Because we have to make some balance of forces here. We have to express this as an area, as a surface integral. But then if you remember our video in the mass conservation equation, that we use the divergence theorem to express surface integral in terms of a volume integral. So we did something similar here. We do something similar here, that we express a surface integral in terms of volume integral, so we can combine these two contributions from the external forces. acting on the fluid. So this is our integral momentum balance. And then we will make use of this equation, which is known as the transport theorem. So you can find this equation in multiple books related to fluid mechanics. So basically, this derivative, the material derivative of this volume integral of the quantity of the momentum, can be expressed as this equation. So basically, we introduce the material derivative inside the integral, and then this material derivative is expressed as this. So now we can also introduce these contributions. We pass these contributions to the left-hand side of the equation, and then we combine the integrals. So we will get something like this. So this integral momentum balance, this total volume integral of this integrand has to be equal to 0. But the only way that this equation becomes 0 is that if the integrand is 0. The volume cannot be 0 because we are considering that it has a finite volume. So in order to satisfy this equation has to be equal to 0. So that means that the acceleration of the fluid has to be equal to the forces acting over the fluid, which is going to cause a variation in the momentum. So this is the differential equation, the partial differential equation that expresses the momentum conservation equation for a fluid. So as I said before, we have a temporal variation of the momentum, we have a spatial variation of the fluid, of the momentum of the fluid. So we have spatial changes of the momentum in the direction of the fluid, in the direction of the flow, or the variation of the momentum as the fluid moves. These two accelerations are equal to external forces acting on the body, such as gravity, plus the internal forces, which can be the pressure and the dynamic stresses of the fluid. So we are particularly interested in studying incompressible fluids, such as liquids. So that means that the density is not going to change with position, and it's not going to change with time. So this equation becomes like this. So we just basically take out the integral from the differential, from the derivatives, and we obtain something like this. And then now let's assume Cartesian coordinates. That means that the velocity will have components in x, y, and z direction. So this system of equations, this is an equation that represents a system of three partial differential equations. So you can see here that this equation is very complex, mathematically speaking, because we have plenty of derivatives that are strongly coupled. Because in order to obtain the velocity field in x direction, you also need to know how it varies in x direction, but this velocity in x direction is also going to depend on the components of the velocity in y and z direction. So these terms are nonlinear, are highly nonlinear. So it's really complicated to get an analytical solution for these equations. And also here you need to introduce the total stress tensor into here in order to obtain an equation for the specific fluid you are interested in. So we will talk about this. So now I want to talk about Newton's law of viscosity, which is used to describe Newtonian fluids, or which are the fluids, the most simple fluids that exist in this world, such as water. So a constitutive equation describes how a material will react once a force is applied to it, or a stress, and thus when the fluid is moving. So Newton's law of viscosity is the constitutive equation that is used to describe fluids like water and air, But here we will only be interested in studying liquids, so we will only consider the case of water. So some features of Newtonian fluids is that when a Newtonian fluid is at rest, the stress is hydrostatic, and the pressure exerted by the fluid is the thermodynamic pressure. So this basically means that, for instance, you remember that I said that this tensor, the stress tensor, is associated to the dynamic movement of the fluid. So when the fluid is at rest, this contribution to the total stress is going to be zero. So the only stress that is present in the fluid is the fluid pressure, the hydrostatic pressure. And then, yeah, you remember that I mentioned that we were going to explain this this tensor, this mathematical representation of the stress tensor of the fluid, of a specific fluid. So for the Newtonian case, for fluids, for simple fluids, this stress tensor, which is associated to the dynamic contribution to the flow, is going to adopt this form. So we have a constant, which is known as the viscosity, and then we have this another tensor, which is known as the deformation tensor, which can be calculated simply as the sum of the gradient velocity and the transpose of the gradient velocity, and this sum divided over 2. So this contribution is known as the viscous forces. So viscosity can be seen as the fluid resistance to flow. And the higher the resistance to flow, the higher the value of the viscosity. And this, you remember, this is an stress. So this means that this is also an stress, which is equal to a force per unit of area. So this term is known as the viscous force, which in a fluid, in a Newtonian fluid, viscous forces are proportional to the rate at which the fluid velocity is changing in space. And the constant, the proportionality constant, is the viscosity. So for Newtonian fluids, the viscous stresses arising from its flow are at every point linearly correlated to the deformation tensor. So this is a linear equation. So I will show to you in a second how these equations take the following form. But I just wanted to say that when the fluid is at rest, this tensor, this matrix, is going to be equal to 0. But when the fluid is moving, when the fluid is flowing, this term becomes more relevant. So it will have a contribution to the total stress. So the total stress will now be the pressure plus the dynamic part of the stress. For Newtonian fluids, this is the stress tensor is a linear relation that relates stress with the deformation tensor, and the constant of proportionality is the viscosity. So let's say that let's assume that mu is the fluid's viscosity, which is going to be constant, and sigma is the contribution of the stresses when the fluid is moving or on the flow. So the total stress, as I said before, this is a tensor which can adopt the form of a matrix of 3 per 3 elements. So the total stress is going to be equal to the pressure, which is only going to be relevant in the diagonal elements of the matrix. This term is this one, and then plus the viscous forces. So we have the viscosity, and then we have 9 elements which have to be estimated as this. So if we know the velocity field of a fluid, we can obtain the velocity gradient, and then once that we have the velocity gradient, we can estimate this deformation tensor, which is going to take this form. So this is the gradient velocity, which calculates the variations, the spatial variations of the velocity of each of the components of the velocity field. So for instance, here in the first row, we have the variation of the velocity in x direction in x, y, and z. And then here in the second row, we have the variation of the velocity in y direction, how it varies in each of the directions of the Cartesian coordinate system, and the same for c. So what does these components mean? So these components of the gradient of the velocity estimate the deformations. So that's why it's called deformation tensor, because it will give us an idea of how the fluid is being deformed. So as you can see, the elements, the diagonal elements of this matrix correspond to equal indices. You can see it here. So deformations with equal indices are the extensional deformations, which measure how the fluid is being deformed in the same direction. So here we have a cube, and then we are stretching it in x direction. So the shape is not going to change, but the volume does. So for those kind of deformations, we have extensional deformations when we stretch the fluid in this direction. We can also stretch it in y direction. So now this length is going to be modified, but we can also have deformations in C. So these elements are going to tell us in which direction we have extensional deformations. And the elements outside of the diagonal correspond to shear deformations. So for instance, instead of stretching the fluid in this direction, we are going to apply a force over this surface, but we will stretch it also in x direction. But instead of a change in volume, we will change the shape of the volume control, and the volume is going to remain the same. So for those kind of deformations, we call this kind of deformations as shear deformations, when there is going to be a variation in the angle in the y direction. So the force is being applied over this surface. We apply a shear force here, and we are causing a shear deformation, which can be represented at this figure. So yeah, here I'm representing the case the variation of the velocity in y direction. The variation of the velocity in y direction, how it varies in the x direction. So we have this term, but it's going to be we can also have deformations, for instance, in c direction, as they are being indicated by these indices. So you sum the gradient, the velocity gradient plus its transpose, you get the deformation tensor. So for Newtonian fluids, for fluids such as water, extensional deformations are always zero, because these kind of deformations are only relevant when you have materials that behave as springs, as elastic materials. So in this kind of materials, they tend to follow Hooke's law of elasticity, which is the phenomenon when you stretch springs, and these springs can return to its initial configuration. So this kind of extensional deformations are more relevant for those kind of materials. So that means that for simple fluids such as water, we will only have this kind of shear deformations. And here you remember that we have this equation. So this is a tensor equation, a matrix equation. But in the majority of the cases in simple flows, Newton's law of viscosity can be expressed as this equation, which is it's a scalar form. So for Newtonian fluids, you have a linear relation between the shear stress and the shear rate. So shear rate, you remember, measures this deformation with this derivative of the velocity in y direction, how it varies the velocity in y direction in x direction, and then you plot it against the force that is being applied over this surface, and then you will always have a linear relation, and the constant of proportionality is the viscosity. So the higher the value of the slope, the higher the value of viscosity. So, for instance, we have a linear relation with a slope mu1, another one with mu2, and another one with mu3. So the viscosity for Newtonian fluids can only vary with temperature, pressure, and concentration of the species. So in the case that we have constant temperature, constant pressure, and constant concentration, the viscosity is always going to be constant. Doesn't if the velocity gradient varies. So this is another characteristic of Newtonian fluids, that the viscosity is constant as long as the temperature is constant. Here, for instance, we have three different values of viscosity, but this curve can represent when the temperature is 20 degrees, this one with, no, the opposite case. With this curve, this curve represents the case when the viscosity is equal to 20 degrees, this for 30 degrees, and this for 50, because the viscosity decreases with an increase in temperature. Newton's law of viscosity can also be seen as a diffusion equation. So if you are familiar with heat transfer or mass transfer, you can notice that Newton's law of viscosity is similar to Fourier's law or to Fick's law. So diffusion is this physical phenomenon where there is a transport of the quantity of a property, for instance, temperature, momentum, or mass. So there is a transport of this property within the fluid. This is in contrast to convection, which is the transfer of a quantity from one place to another due to the movement of the fluid. But in diffusion, we don't really care about the movement of the fluid. We care more about how one property is being transported from one place to another place, and this transport by diffusion always goes from high concentration of the property to low concentration of the property. So this means, for instance, in heat transfer, the transport by diffusion of heat always goes from high temperature to low temperature. It never goes in the opposite way. You never transfer energy from low temperatures to high temperatures. It's always from high to low. The same happens with mass. So mass is being transported always from high concentrations to low concentrations. And with momentum, we have something similar. So momentum is always being transferred from high velocity regions to low velocity regions, and this transport of momentum is special. So we are interested in studying how the velocity varies in y direction, and there is going to be a physical property of the fluid that is going to oppose to this transfer of momentum, which is the viscosity. So the shear stress, can be seen as a diffusive flux of momentum, which is the force per unit of area that must be applied to generate the shear flow. So that means that in order to obtain this shear deformation, you must apply a shear stress here, which is this one, and this is going to be equal to the product of the viscosity or the resistance or the resistance of the fluid to flow or to being deformed, multiplied by the gradient of the velocity or shear rate to make the fluid flow. So Navier-Stokes equations. So the Navier-Stokes equations express mathematically the momentum conservation and mass conservation for Newtonian fluids. So Navier-Stokes equations are actually a system of four partial differential equations, because you remember that momentum conservation here is written in vector form, but this equation represents three equations, and then you couple it with the continuity equation. So you have four variables, which is the components of the velocity in x, y, and z direction, and then you have the pressure. So you have 4 equations and 4 variables. So how do you derive equation, the Navier-Stokes equation? So these equations apply for for Newtonian fluids. So you must introduce this total stress tensor into this equation that we obtained for an incompressible fluid. And then I skip the math, the algebra, but if you introduce these equations into here, you obtain the following equations, where you have the contribution of the gradient pressure, which corresponds to, for instance, external forces by the action of a mechanical machine. It can be, for instance, a pump. This term is relevant when you are transporting water from one low place to a place at the top of your house. Then we have a Laplacian here, which corresponds to the viscous forces. So you have the viscosity and the second derivative of the velocity. So this term of the equation is known as the diffusion. And then if we consider only the action of gravitational forces with constant physical properties, you have the contribution of the gravity. And then let's assume Cartesian coordinates. So that means that the velocity, we have components of the velocity in x, y, and z directions, and then we obtain this system of equations that you can see. They are very complex because we have temporal derivatives, we have spatial derivatives, non-linear terms because we have a multiplication of the variable multiplied by derivatives of the variable. Then we have another gradient pressure, another derivative for the pressure, and then you have a Laplacian, that means a second derivative of these variables. So these equations, you probably have heard about them. Those equations are considered as one of the 7 millennium problems. So if you get to prove that these equations have a solution and this solution exists, you can get $1 million prize. Yeah, these equations are really hard to handle because of their mathematical complexity. And if we ever find a solution to these equations, the solution of these equations will have major implications in our society because we can solve a lot of problems associated to meteorology, aerodynamics, flows applied to the industry. So these equations are really important to our society. So that's why CFD exists, because in CFD we treat these equations and we try to find not analytical solutions but numerical solutions instead. So we applied very sophisticated numerical methods to find an approximate solution to the original system. So one way to work with these equations is that you focus on a particular problem. So you start to simplify the problem, and then the majority of the derivatives can be ignored, and then you get a simplified system of equations which can be treated much more easily compared to the whole system. So the goal of CFD is to find numerical methods that can solve this system of equations. So just to conclude, I want to show you some similarity of these equations with other conservation equations. So I mentioned before the Fourier's law, which is used to describe the heat transfer by diffusion. So in heat transfer, we study the variations of the temperature spatially, and then we have this constant, which is the thermal conductivity, and the heat is the heat that is being transferred from one body to another is given by the product of conductivity multiplied by the temperature gradient, which you can notice is very similar to Newton's law. of viscosity. And then we also have first law of thermodynamics for fluids, which tell us that the internal energy of the fluid, which is given by this product, by this sum of terms, is going to be equal to work plus heat that is being transferred to the fluid. So we have also a variation of the temperature with respect to time. So this is the fluid density, this is the heat capacity of the fluid, and then you multiply we are assuming here that these values are constant, but we can introduce them into the derivative, and then you will get some sort of enthalpy or some sort of energy of the fluid. So the energy can vary with respect to time, but it can also be transported by convection in the direction of the fluid velocity. And then this internal energy is going to be the only way you can modify the energy of your fluid is that if you apply some work into the fluid. So, for instance, you can also modify the energy of the system if you apply some mechanical work. So you can also there can also be some loss energy into the system. So this energy has to go somewhere. So you quantify these energy losses using this term, which is known as the dissipation term. And then this is the heat that is being transferred into the fluid. In mass transfer with chemical reaction, or mass transfer, for instance, in a mixture, you can have a mixture with multiple components. So, for instance, you can have water, sugar, and coffee. So sugar can be a species A, coffee a species B. You can also have multiple components. So how the particles of the coffee or of the sugar are being transported by diffusion? So they follow fixed law of molecular diffusion. So this is a mass flux of sugar, let's say, which is going to be equal to a coefficient, which is the diffusion coefficient of sugar multiplied by the spatial variations of the concentration of sugar. So as I said before, in this kind of equations, the mass transfer or the flux of mass always goes from high concentration to low concentrations. So for instance, let's say you have coffee or sugar in your cup of water, hot water, and then you add with a spoon some coffee at the top of your mug, or your mug of coffee, cup of coffee, and then if you don't apply a mechanical force and you let the coffee at the top of the water, and then you will see that the coffee is going from the very top to the bottom of the mug. So that's diffusion, because a higher concentration of sugar or coffee will be seen at the very top of the mug or of the cup, and then it will be transported towards the bottom of your cup of water, hot water. So that's molecular diffusion. And then the mass conservation is given by this equation, which you can notice is it is also very similar to this equation. So we have a temporal variation of the concentration of the species A plus some convection. That means the transport of the species A due to the fluid movement, which this is going to be equal to the diffusion, transport by diffusion of the species A, and then you add some source term, which can be a chemical reaction. So there might be some changes in the system that can modify the concentration of species A. So those changes can be caused by a chemical reaction, which is represented by RA. So with this, I conclude this presentation. So I just want to mention that In the next video, we will be solving these equations, this complex system of equations for a very simple flow, which is known as simple shear flow. So we introduce a simple fluid, such as water, between two parallel plates. So the plate at the bottom is going to be fixed. The plate at the top is going to be moved with a velocity uv. And then we will assume density and viscosity values, constant viscosity values of viscosity and density. And then we will assume isothermic flow. That means that the temperature is going to be constant, and then we will only consider the spatial derivatives. We will ignore the temporal derivatives. So under these assumptions, these equations can be solved. So in the next video, I want to show the solution, the analytical solution that can be obtained for this flow using the Navier-Stokes equation. So thank you everyone for staying until the end.